Good morning. Today we're going to start talking about Chapter 16, and that deals with chemical equilibrium. We're going to include 16 and 17 in this unit. We're going to try and get through as much of it as we possibly can, and hopefully we get it in before the end of the school year. Yesterday you had an assignment that talked about reversible reactions, and all I really wanted you to do was to try and figure out what is the difference between a reversible reaction and a forward reaction. And hopefully what you got out of that is that in a reversible reaction, you have reactants and you have products. And as the reactants are going to products, my products are also going back into reactants. So at any given time in that reaction, we have a certain amount of reactants and a certain amount of products. When that reaction reaches equilibrium, the amount of reactants going to products and the amount of products going to reactants stabilizes. And those amounts, those molar amounts, won't change in a reversible reaction. When that happens, we say that it is at equilibrium. In a forward reaction, for example, this is the combustion of methane. In a forward reaction, it's a one-way reaction. My methane adds to oxygen and it yields carbon dioxide and water. That is a one-way reaction. That carbon dioxide and water is not going to turn back into methane and oxygen. Okay? So in a reversible reaction, we have reactants and we have products at the same time. They're not in the same amounts, they're in different amounts, but they're recurring at the same time. This reaction is moving forward and it's moving backwards. It's going from the reactants to the products and from the products to the reactants. And a forward reaction is just reactants going to products. So that brings us to chemical equilibrium. By definition, this is the state in which the concentration of the reactants and the products remain constant with time because the rate at which they are formed in each reaction equals the rate at which they are consumed in the opposite reaction. Okay? So reactants going to products, products going to reactants, the amounts that those are taking place or the molar amounts that those reactions are happening at will stay constant. When we're writing chemical equilibrium, okay, what we want to be doing is talking about expressions. There is a general form for an equilibrium expression, okay, and that basically is that we will always take the concentration of our products and divide it by the concentration of our reactants. To make an equilibrium expression, you will often see the general equation AA plus BB yielding CC plus DD. So what does that mean? Well, my products are C and D. Okay? The little number, the little letter, stands for the coefficient. The capital C stands for whatever that compound is. Okay? So if I'm going to write this expression, this generic expression, it would be a capital C. And then the little c, the coefficient, will be to the power of C. Then capital D to the power of little d over the concentration of reactant A to the power of little a times the concentration of B to the concentration of little b. That's how you write an equilibrium expression. So let's look at the worksheet on 16-2 and let's try problems 1 and 2. For problems 1 and 2, when I'm looking at this expression, I'm seeing that they are all gases. And that's important because only gases and aqueous solutions can be put into an equilibrium expression. Liquids and solids will not be put into an equilibrium expression. So let's take a look at the first one. The first one, I have my reactant of water, and then I have, my product of water and my reactants of hydrogen and oxygen. Okay? So let's start by taking my concentration of H2O, and there's a coefficient, so it's squared, over my concentration of hydrogen, and again, there's a coefficient, so it's squared, times the concentration of oxygen. No coefficient, so there's no exponent. Okay? This is the equilibrium expression for the electrolysis, or for the synthesis of water. Okay, let's look at the next one. Write the equilibrium expression for the formation of nitrosyl bromide. Okay, they're all gases, so I know that I'm going to put every one of them in the expression, and I'm going to start by taking NOBr, the concentration of it, squaring it, and I'm putting that over the concentration of NO squared times the concentration of Br2. Okay, no coefficient, so it's not squared. Let's jump over and let's look at one that maybe isn't a homogeneous equation, that we have different types of compounds. For example, look at number 10. Notice that tin oxide is a solid and tin is also a solid. Therefore, they are not going to be found in the chemical expression. Okay, in the equilibrium expression, you will not include those. So the equilibrium expression for this equation is simply the concentration of CO2 squared over the concentration of CO squared. Okay, that's all we do. Please make sure that you understand that the square brackets mean concentration, and that you always use the exponent as the coefficient. If you have any questions, please feel free to contact me. Hope you're all doing well. Miss you guys.